is mixing this water which is entering there, and produces this dense water. This dense water is has higher or lower salinity. Higher or lower salinity means higher or lower density. So the Adriatic produces, in function of whether the circulation is cyclonic or anticyclonic, produces higher density or lower density water. What consequences have these things? This is this example without the schematic circulation, and this is a situation what I already showed you before with showing also the similarity between drifter reconstructed flow and the geostrophic flow. If the Adriatic is releasing the high density water, what happens? It finds here the density at the bottom, density which is of lower density with respect to this water coming there. So what is happening is that at the bottom there is a density gradient or pressure gradient in such a way that it points from the border toward the center, because you have a higher higher density along the border, and this is a higher pressure at the border. That means that there is in this kind of situation where there is an inflow of a lower density water, you are creating at the bottom, you are creating the pressure gradient which creates the geostrophic flow in the opposite direction. So with this kind of pattern in the surface, in the anticyclonic circulation at the surface, at the bottom, in the bottom layer, there is a cyclonic circulation. So you have really a two-layer system which is created. And vice versa with the cyclonic circulation. In the surface cyclonic circulation, the bottom layer is anticyclonic because of the changes of the pressure gradient. You can see that the pressure gradient here is from center to the boundary, but at the bottom is from the boundary to the center. So you have changes of the density. This evolution is clear, and we constructed a simple parameter which is the difference between density, between sea level, between these 2 points. If you do the differences in height, sea level height between these 2 points, is practically, what is this? This is practically the sea surface geostrophic flow. The component of the geostrophic flow in this direction is east-west, right? So in this specific situation, the sea level is higher here than there, so the pressure gradient at the surface is from here to there, and the flow is eastward. If we change, this is specifically in 93, 96. Oh, these are flows, which I already showed you. In the situation where there is a cyclonic circulation, like in this case here, the sea level is higher here than the center of the cyclone. So the pressure gradient is from here to here, and the flow is westward. Okay, so it's a very simple parameter which tells you immediately what kind of circulation you have by looking simply at these 2 points and make these differences in a sea level. So you're simply looking at the east-west component of the geostrophic flow, and this is how it looks like. This is another anticyclonic thing, which is 26229. You can see this here. If you go further, you have again the cyclonic circulation. So you can see these I cannot say periodicity, but cyclical changes of the pattern of the circulation in the Ionia, which is associated or which is due to the interaction between the Adriatic and Ionia. So there is a kind of internal mechanism which determines this internal circulation. Obviously, first thing what one would say, okay, but why don't we look at the wind? Because the wind can, by impacting the vorticity in the sea, into the water, can change this vorticity in the ocean. But if you are looking at the wind vorticity and compare this starting from the equation of vorticity, you find out that the values of vorticity and the magnitude of vorticity in the wind field and the sign of the vorticity cannot explain these variations. So the variations are really due to the internal mechanism, due to the feedback between these two basins, thanks to this dense water formation in the Adriatic. So we have done another thing, is that using all the float which have been present in this is southern Adriatic, this is the deepest part of the Adriatic, and we have been looking at the floats in order to find out the temperature salinity data from the float and density. And we put all the floats which are found in the last period when the floats have been used, which were found in an area which is deeper than 1,000 meters, and put them and find out. You see how many measurements points are present there, thanks to the presence of the floats, which are not at the same time, at the different times, but there is a pretty good coverage of the last 15 years of the measurements. And so the thing is that that what we have done is, since as I told you before, there is this feedback between the Ionian and the Adriatic. This feedback means that if you have a certain type of circulation, if you have an anticyclonic circulation, as a consequence of that, the density in the Adriatic will be lower, because there will be entering of the low salinity water into the Adriatic, and vice versa. If there is a cyclonic circulation, the high salinity water would be entering into the Adriatic and will have as a result the formation of the dense water. And indeed, this continuous curve is this difference between these two. So this is what we call the ADT2 minus ADT1. So these are the sea level height 2 minus sea level 1, which if it is positive, the circulation is cyclonic. Anticyclonic, if it's negative, the circulation is cyclonic. So with the anticyclonic circulation, we should have low density, and cyclonic, we should have high density because of the salinity, which plays their important role. And this continuous line is this ADT2 minus ADT1. And these are the points what we have for each year. This is 2010 until 2018, is now last 8 years. And first, at the very beginning, the number of data are rather restricted. There are not so many floats. But as you go further, you can see the number of points, measurement points increases, number of floats increases. And so let's see if these are the average, the mean and standard deviation around it. You can see that the standard deviation is pretty high, because we didn't look only at the data from the winter period, but we put all the data in order not to do any biasing into this thing. And what we have done is we have done the potential density between 200 and 800 meters. Why 200 and 800 meters? We don't want to look at the surface, because surface is influenced by the seasonal heating and cooling, so let's forget about surface. We know that the vertical convection, and Alessandro will confirm that, goes up to 800 meters there. So that's why we have chosen 200 to 800 meters, and this is these are the results. So the result is potential density, average potential density in the 200-800 meter layer, and this is how it changes. So what you can see is that for a low ICI, the Ionian circulation index, the consequence of that, with some time lag, there is the lowering of the density in the Adriatic. This is exactly what we are expecting. And here you can see that they show the similar trend, or decrease or increase. We are going here up to 2018, and we have seen last year that there is changes to anticyclonic circulation. So we might be able to continue this time series and continue confirming this theory. And you can see that the differences between these 2 points, as far as the sea level is concerned, is around 4 to 5 centimeters. It's a pretty large sea level differences. The salinity, the water density changes from 29 something up to 2900. It's like a 1% is change, interannual change of the seawater density. So this is an example how you can use all these data to do some specific studies. So we have combined here satellite data. We have combined here Lagrangian float measurements. Although we haven't used these Lagrangian float measurements, we have used them as almost as Eulerian type of measurements, because we defined our area, such a large area, and we did these averages, all these averages, this point here, certainly doesn't contain a single point, but contains a number of points which are not necessarily at the same location, but they express the same physical reality of the process what we are doing, we are considering. Let me see what. Okay. This is another. We extend this time series. You remember we were looking here in the first part here, where we used the float. Before this period, more or less, in this old period, we don't have the float data. There are no floats. There were no floats. But what we had available are the cruises, the ship cruises. So the ship cruises in that case are not so many point measurements, but there are very few. And the measurements typically has been done across the Adriatic with a single transect. And each of these points, which are the salinity and temperature, each of these points are the average of whatever has been measured on shipboard measurements from 200 to 800 meters in an area which is deeper than 1,000 meters. The same criteria as we applied for the flow data. Again, still here you can, this continuous line is the differences in a sea level between this point and that point. And What is this? What is this? Here is density. You can see this is the density. Number of points certainly is smaller than in the case of flow data. And this specific period is anticyclonic. Here is cyclonic and anticyclonic. What is clear is that how the blue and red curve follow each other very nicely for the much larger period than when we are talking about the float period. And you can see that the decrease of the ICI, so the ICI positive, you remember, means that this minus this, that's anticyclone here. Then we have the low ICI is low density, which is the opposite situation, and so forth. You can see how they follow very nicely each other. Here are the average. Here are the average sea surface pattern, which illustrates the type of circulation what we have. Yeah, this is that's it. What else? No, nothing else. There are. So that's what I wanted to tell you, just to give you an idea how we can use in a real oceanographic life, how do we use the data what are available to confirm or not the hypothesis or theory what has been defined. Let's see. Okay, so now you can go. We can go with our instrumentation lectures. I like always the instrumentation by themselves is not something which is not very exciting, at least for me, unless we really know how to use them. I mean, unless we know what kind of information on the physics of the ocean we can take it. The same thing is when we are talking about the numerical solutions or analytical solution of the equations of motion. Whenever we are talking about that, it's not the solutions are not the final goal. The final goal are understanding the physics. So we understand the physics, or by doing observations, by using the instruments and our theoretical knowledge, or by doing the numerical modeling and trying to understand the physics, or by finding the analytical solutions and then understanding the physics. Because the analytical solutions are not a pure mathematical exercise. It's also, apart from being a mathematical exercise, is also trying to help us to understand the physics which is behind it. So the same thing applies to numerical instrumentations. So don't forget that the instrumentations are something which we are using to understand the physics. You can also work on instrumentation, but that's another story. And let's see where we were last time. This is the deployment of the profiling floats from research vessels or from the ships of opportunity. Ship of opportunity, as I told you before, are commercial ships where you ask crew members to deploy for you. You don't have to be present there because they just have to write down the position where they deployed, and then they communicate the position, and after that they are free. So they can do it also on during the navigation. The ship doesn't have to be doesn't have to stop. These are all information of TS and profiles what we have already seen before. You can see here what kind of profiles we can obtain from the number of data what we can obtain from these flows. This is, you know, the temperature. You can see the evolution of temperature. TS diagram, so the diagram which shows the dependence of the temperature and on salinity, and you can see how they presented that here are lines of equal density, isopycnal lines, and all these things has been obtained from a number of measurements by flows in this area here between Sicily and the Majorca island in Spain. This is something, or Sardinia, sorry, not Sicily. On the basis of profiling floats, which is here as ProWar. You remember that ProWar is one of the sample of these one of the two types of profiling floats which are available at the market. They are essentially doing the same thing, and you can do this kind of diagram where you follow the float and you construct the time depth diagram, which where that each time corresponds to a certain position, and so you can see the evolution of the vertical profile of density, for example, in a function of time, or and also in a function of the position. Here, that's certainly here. You can see that the depth here is relatively low. This is the Sicily Strait, and it goes westward, and you see how the density behaves, and then there is this pycnocline, and here is the sea surface density, relatively low surface layer density. And the question is now the float has been deployed here, and you remember that when we were discussing about the floats used in the Mediterranean experiment, Mediterranean Argo experiment, the floats have the depth where it stays is 350 meters. And you remember that we said, okay, why 350 meters at the surface is where the float are moving with the current? Because we want to study the dispersion of the Mediterranean water. And so, if we know, so that means that certainly this float, what has been deployed here, will be moving westward, because the 350 meter is the depth where the Mediterranean water is spreading. And the spreading is specifically at the westward, because this water has been formed in the Eastern Mediterranean and has a higher salinity, and then spreads westward and then finally exits in the Gibraltar in deeper layers, underneath the Atlantic water, which enters there. So this is why these guys moves westward. Certainly it does move as along the straight line. It has the something what I mentioned you before in the ocean. There are a whole series of scales, special scales, and one of these are mesoscale eddies, and you can see the sign of the presence of the large eddy here, close to the North African current. So number of information you can get simply by looking at the pathway, at the trajectory of this eddy, and at the vertical and horizontal distribution of temperature and salinity. This is the salinity which comes, and this is the temperature. And here you can see that there is this part here is warmer than the one. Then hold this thing here. Why is warmer? Why is warmer? Because if you look at the time when the float was present in this specific part here is this is the beginning, this is the end, and so this is that's the period when it was September, October, when there is a warmer surface area. So you have to take into account that this is not that they are not simultaneous synoptic measurements, but they are also in different parts of the year. And this is why, if you want to look at the behavior of the water column where there is no seasonal signal, there is no seasonal heating and cooling, it's very useful to look at the part which is below 100 or 200 meters, as we have been done in the Adriatic. You remember that we eliminated the first 200 meters because we are not interested in seasonal heating. We were not interested in seasonal heating, but only in the consequences of the vertical mixing, though. So that means on the interannual variability. And this is the profiling flows in the world ocean today as part of the Argo program. You can see that these are the 3,600 floats which were present 15 December 2013. They look pretty dense, but you know, if you consider that we are talking about thousands of kilometers of the ocean surface, this is not really so huge number as it could be. One of the first, it's interesting, one of the first experiment which was not planned, but it has been done is, I don't remember exactly when, but it was in, I think in 60s. There was a commercial ship transporting from China to Europe, I don't know, plastic ducks, you know, and there was thousands of plastic ducks, and there was an incident, and the ship was lost all the ducks. So the ocean was full of these plastic ducks. And there was a possibility to look at the drifting of these ducks all over the world ocean. And I think I don't remember if somebody has a connection with the internet. I think the thing was the thing happened someplace in the Atlantic. But these plastic ducks has been found all over the world ocean after years. So this is the first not planned drifting experiment which has been done, and it was nice seeing the distribution of these plastic ducks over the world ocean as a after this experiment. If you go and look into the internet, you can find the drifting ducks or something, you know, you can find it. This is the Medargo float position in my profiling floats in the Mediterranean. You can see that this is the international program where there is all different countries present. And here are the floats which were present at 15 December 2013. And part of these has been used for the calculations of the mean density over the Southern Adriatic, what I present to you before. And you can see also there are a number of floats in the Ionian. Obviously depends on the country who is interested in which position is interested. You remember the Black Sea and how these floats were traveling in a cyclonic way all around the Black Sea, and they helped to have a good description of the flow in the Black Sea or in general. Then we have gliders, which are underwater. All these autonomous systems do not need the presence of a man directly at that. So this is the glider, are driven by positive or negative buoyancy created by a change in the volume. There's a change in the volume, which then ends up in the fact that there is no propeller is required. You just simply change the volume, and it goes or down or up, but doesn't go vertically because it has aids, and then they're movable, so they have vertical pins and horizontal, by which they determine not the vertical movement but slope movement, deeper or up versus surface. And here is battery and buoyancy control. This thing here, this is the antenna by which the guy sends the data to satellite. And winds convert vertical velocity into forward velocity. That's important. It's like an airplane. To change direction of the glider, a rudder is used, or internal mass is rotated, so that simply changes the internal mass. Glider moves downward and upward in a sawtooth pattern. So it goes this way and then goes this way. And so progresses and goes up and down. And this is what to say. This is how it looks like in the sea. It has here is the video how it moves. You can see how, and each time that it stays at the surface, sends the data to satellite and then to the data center. It has 1 kilometer or 200 meters and depth. Has a 2 to 5 kilometer between surfacing. So every 2 to 5 kilometers goes to the surface and goes and sends the data. Horizontal speed is 20 to 40 centimeters per second, while the vertical is 10 to 20 centimeters per second. So it's pretty fast. It takes about to cross the entire Adriatic. It takes about 3-4 days. The cross section, no, not the long, not cross section. These are the sampling characteristics, and then you decide what kind of sensors you put on it, or temperature 70, obviously. You put also the nutrient sensor, oxygen, chlorophyll. What about they can be used also to a certain extent also to give the information on the horizontal flow, because if it shows drifting, then you can understand something about the horizontal velocity. But this is not the main application of the. This is the. They have this near real time data transmission. This is very important. This is the cost of these guys. It's like a 60 to 70,000 euro. I think this is much more now, because this is it depends also. To see this produced in the States, it depends on the exchange rate between dollar and euro. It used to be this when euro was very expensive with respect to dollar. This its thing is that it has a near real-time data transmission. Every surfacing sends the data, which is very, very good. Has the optics, Seabird, CTD measurements, oxygen, and this is not expandable, so we are not supposed to lose it, because it's probably better not to lose it, although sometimes it happens, unfortunately. This is how they are deployed from the very small boat, and these are for example some data which has been collected along the coast of Spain, and these are the A, B, C, D, E. These are the, and goes back. And so you can see here. You can see here the. This is the. That's the temperature as a function of. I think it's temperature. Yes, this is the temperature in function of time and depth. Again, time and depth, because of you always have to transform this into the position. Indeed, you can see here there are the positions, but there is also time, and the position is determined when it is surfaces. Then you determine the problem density. You can see the various structures which are associated to the current, to the transport of the warmer water across the transect. What it does, for example, these high temperature blocks are due to the northward current, which goes that way across the transect, which has been done. The thing is that thanks to this high resolution, and you can see it here in this specific case, it has 3,200 profiles along all these transects. It can resolve large meso and small scale processes, because thanks to this high resolution, you can see both large meso and small scale processes, where you know that large scale processes in the Mediterranean are on the order of 8,000, 100,000 kilometers, or the mesoscale are on the order of 50 to 100 kilometers, while small scale processes, which are sub-mesoscale, which are on the order of a kilometer or 10 kilometers. So you can resolve all the spectrum, all the wave number spectrum of these measurements by using gliders. And this is, for example, this is for a specific period. How you can see that they used to have 7 gliders, while we are 6 gliders simultaneously. So they are doing various transects in order to obtain quite a synoptic view over the larger area. And then obviously there are a combination of various other measurements which complements these data, like gliders, floats. These are the float measurements. These are XBTs and CTDs. You remember XBTs now, those which have been used to make temperature measurements from commercial ships, or CTDs. Those are mainly from the oceanographic ships. And so, for a specific period, you can see how good is the coverage, the spatial coverage of this relatively small area. But simply looking at the density points, measurement density points, for example, the floats, which are here in the green, you can see, for example, this group here of point measurements. Since you know that the float are moving by the current, this circle certainly corresponds to a mesoscale eddy, okay? Because the float was start to move probably from here, then enter into the eddy and get trapped there for some time, and then follows what is going on in the float in a eddy. Here, it's another very nice thing is the semi-permanent or almost quasi-permanent Alboran gyre, which is also described very well by the float, by a float which has been trapped into these structures. Okay. Obviously, these are the planned measurements, because these are so perfectly aligned. So this is, and in fact, if you look, these are the XBT and CTD. So that means they're from the ships. But whenever you have these Lagrangian type of measurements, they describe pretty well what is happening as far as the circulation is concerned, directly by looking the qualitative behavior of these things. Then we have autonomous submersibles. They are self-propelled vehicles that can be programmed to follow a predetermined driving path. So they are another autonomous type of instrument. And here is some future evolution, because the oceanography is a continuous evolution. You can see what kind of measurements will be done. You can see the instruments which goes up and down, do the measurements of the profiles, the gliders, everything. And then you can see also there are bottom-mounted instruments which measure the sea level, for example, and which send the data through these sensors, which then sends the data to the satellite. So the automation makes always makes all these things very good, and what is the most important thing is this near real time. Why near real time is important? It's important if we combine these measurements with the numerical modeling, then there is a good chance to do the good efficient prediction in the ocean. And as it has been done in the atmosphere, and you know that in the atmosphere, you know very well that there is these cyclones which are formed, which are responsible for the weather, at least in mid latitudes. The same thing applies to the ocean. There are cyclones which are there, or anticyclones, which determine what we say weather in the ocean, because equivalent to the atmosphere, we have weather in the ocean. So might be useful in the future to do the prediction, weather prediction in the ocean, which is now, and weather prediction in the atmosphere is based on a near real-time data, data transmission, which then are put integrated into the model, prediction model, and the same scope, the same aim is in the ocean. Obviously, the application is not as immediate as in the atmosphere, but certainly more we are oriented toward the use of the ocean, clever use of the ocean, I hope, more we need the weather prediction in the ocean. Okay. This is the science fiction thing. I'll skip over that because I don't know what to say. And let's go. Let's start with the third lecture, which is this thing here. Okay. So we are now at the point. Before we were talking about the autonomous system. Now we are talking about the in situ remote sensing. In situ remote sensing. So it's kind of a contradiction to itself. It's in situ and remote, which are combined to. One of these in situ remote sensing instruments are acoustic current meter and acoustic Doppler current profilers, which measure in situ, but then you have possibility to have the remotely the information on the measurements. Then there's acoustic tomography and thermometry, and then finally is HF coastal radars to measure surface currents and waves. You will see later on that these specific, especially these HF coastal radars, are very nice tools to do the high resolution measurements, to do the measurements on the order of a kilometer or even less. It depends on the frequency of these coastal radars, which has been used. But we will talk about it further. These are acoustic current meters, which are which are based on the principle that sound is compression wave which travels with the media, and have two orthogonal sound paths of approximately 100 millimeter length with the receiver transmitter at each end. So electromagnetic and acoustic current meters have no moving parts and can therefore take measurements at a very high sampling rate. That's very good, because the classical instrument, they have a rotor which measures the speed. So they are useful for not only for the measurements of ocean currents, but also for wave current and turbulence measurements, because they can be very small. And then they can measure very small scale processes, and there are some measurements on in the bottom boundary layer where the current meters are so small that their dimensions are small enough to pick up the length scale, turbulence length scale in the bottom boundary layer. Then we have the acoustic Doppler current profiler, which is, as you can see, operates on the same principle as acoustic current meters, but have transmitter and receiver in one unit and use the reflection of the sound wave from drifting particles. This is very important. That the ocean has the particles which are diluted in the water, and thanks to those particles, which they play the role of the reflecting body, and then the movement of these particles the movement or reflection of the sound of these particles gives us the information on the movement. If sound is transmitted in 4 inclined beams at right angle to each other, the Doppler current frequency shift of the reflected sound gives the reflecting particle velocity along the beam. Okay, so you have these four transmitters, and a different arrival time indicates sound reflected at different distances from the transducers. So an IDCP provides information current speed and direction not just at one point, but for a certain depth range. In other words, ADCP produces a current profile over the depth. This is very important property of this thing, because it gives you the current profile at different depths. So you obtain instantaneous vertical profile of the horizontal and vertical velocity and but they have different purposes. And deep ocean ADCPs have a vertical resolution of typically 8 meters. So they produce one measurement for every 8 meters, and a typical range up to 400 meters. So at the depth range of 400 meters, they produce like a 50 measurements. And but then they can be designed also for measurements in a shallow water, and have a resolution of typically half a meter and the range up to 30 meters. This is what you have to choose in a basis of what kind of measurements you do. We have done a series long-term measurements, for example, in the inlets of the Venice Lagoon, because for the studies of the flooding of Venice, there was very important to study the exchange between the lagoon and the open sea. And there the depth is around 40 to 50 meters. So you have to pick up the instrument which has this such high resolution and reaches the depth on the order of the depth of the inlet. And the good thing is that these instruments has autonomy for several months. So we used to have these measurements. We used to do these measurements for about 6 years. So we have 6 years of data of each of the inlet of the Venice Lagoon. And since you have the vertical profile, if this is the cross section of the inlet, and if you have the measurements at a certain number of points, what you can do, you can reconstruct the profile of the entire current in this kind of channel, and by doing some simple assumptions. One of the assumptions which helps you very much is that the flow here is zero. The flow is zero at the boundaries of the channel. There cannot be flow different than zero. So you allow that your current at a certain point goes to zero in a logarithmic profile, because this is good approximation for the velocity near the border. But if you have more than one measurement, this is even better. Better reconstruction of the flow. Then you do simply the integration of these. You define your elements to integrate, and you obtain the flow rate. And in fact, we obtain the changes, the flow rate as a function of time in Venice Lagoon inlets, in different inlets, and how they are in function one to another, and what is the And apart from getting the information on the flow rate, on the current speed, which is on the order of, can reach 1 meter per second, which is very, very, very high flow. This is associated to tide. So we have a tidal signal which determines these oscillations of the current, inflowing, outflowing current into the Venice Lagoon on the order of 1 meter per second is the maximum, or the amplitude of that. This kind of information then you can use in order to get the prediction of the high tide in the Venice Lagoon, for example. So this is the correct, concrete approximation of the concrete use of these ADCPs. Another thing is applying the same technique, but in this time in an Otranto Strait, the opening of the Adriatic, or any other thing. You put number of ADCPs, do your measurements for each moment of the measurements. You reconstruct the flow pattern. You reconstruct, calculate the flow rate, and you obtain also how the current is distributed. And this is where this, you remember I showed you the profile, the vertical transect of the flow, and we obtained that there is a inflow here in the Adriatic, and here is the outflow from the Adriatic. And this has been obtained from these kind of ADCP measurements. We obtain also that the total transport out, in, or out, they have to be equal. One inflow has to be equal to outflow on a longer time scale. Otherwise, its sea level in the Adriatic will increase. We obtain that the total amount of water which exits is on the order of 1 million meter cubic per second. This estimate has been obtained thanks to use of the ADCPs. So we had like four ADCP moorings across the Otranto Strait, which gives us the possibility to calculate but not only that, you can obtain you can estimate the outflow rate of this dense water, what I told you before, which then determines the changes of the flow in the Ionian Sea. And if you decide, okay, my water which outflows has the density of 29.2, so you limit your area where this dense water outflows, and say, okay, this is my water which outflows and which is the dense water formed in the Adriatic. And so from the ADCP measurements, I have the distribution of the outflow component of the current, and then I do my integral over this specific area where the density is larger than a limit, what I know that's the limit of the Adriatic dense water, and I do these calculations, and I obtain that in that case the rate of water which has been formed in the Adriatic, which outflows on average over the entire year, is about 300,000 meter cubic per second. So out of these million meter cubic per second, 300, or like 30%, is this dense water which outflows, which is formed in the Adriatic and outflows out, and then feeds the Eastern Mediterranean, Ionian Eastern Mediterranean. The rest, these 700,000 meter cubic per second, are this part here, intermediate one, which is due to the fresh water outflow from the Adriatic and so forth. Okay, so number of exercises using these ADCPs can be done and help the understanding the physics or the physical mechanisms which are important in driving the basin circulation. This is the measurement principle of the acoustic Doppler current profiler. If the object is moving toward, there is the changes of the frequency of the receiving signal. If it's moving away, there is a changing of the frequency that way. And if it's moving across, then there is no change of this frequency. So this is the transmitted impulse is F0. If the object is moving perpendicular to the ray, the frequency is unchanged. Here the frequency is larger than the F frequency of 0, and here it's smaller. So this is a Doppler effect, and this is how it functions. There are some situations when the Doppler current profile doesn't help. If the sea is perfectly clean, if there is no particles at all. But particles can be or anorganic, like something which comes from the rivers or from the land, but can be also organic. Phytoplankton, zooplankton are also helping in doing the measurements. All these organisms which are passive tracer, passively transported by current. There are some complications in that system. Is that if you have a zooplankton is the part of the alive organism in the ocean which moves by themselves. They go up and down following their food, the phytoplankton. So during the daytime they go deeper. During the nighttime they go closer to the surface in function how the phytoplankton is moving. So if you are doing the measurements with ADCP, what is happening if your zooplankton is moving away from the ADCP? You got the artificial vertical velocity of the water, but it's not the movement of the water, it's movement of the zooplankton, and vice versa. If they are moving toward the ADCP, then you have a larger vertical speed that it is really, because there is a movement of the zooplankton. So there should be a way in which you eliminate the zooplankton movement from the signal of the vertical velocity you obtain. Or vice versa, if you invert this thing, by doing the sampling of zooplankton in the sea, you can also determine the biomass of the zooplankton which is present in the sea. So the ADCP can be used not only for doing the measurements of the vertical velocity and the velocity in general, but can be used also on biological purposes, because it helps us to determine the zooplankton presence in the ocean and its vertical movement. The vertical speed is on the order of 10 to the minus 1 centimeter per second, and the zooplankton moves on the order of 1 to 10 centimeters per second. So we are talking about the order of magnitude or even more of the vertical speed due to the associated to the zooplankton movement. So this is the additional use of the acoustic Doppler current profilers. Let me see what shall we. This is the measurement principle, and And here is the you obtain this. It sends this the signal. The particle is in water. This is the direction of current, and then as output of this, you get the current speed and current direction. This is the output. If you have the at the surface, if you have the sensor which sends the data into the data center, then you have a real-time data transmission, which is also another thing. So what essentially we have done in the Venice Lagoon, we put this ADCPs at the bottom. We cannot put it in the middle of the water column because there were ships passing by. And so we got these records every minute or we decide what would be the sampling rate of this kind of instruments. Every 3 to 4 months you have to change the batteries, but this is the only thing what you should do with this. There is a Cryptic Doppler profiler, kind of profiler at the ship mounted. So what it does, this is how it looks like at the research vessel holes, and it does the measurements along the track of the ship, and so it has to be connected to the determination of the position of the ship. So you obtain these the current profiler, the current profiles along the ship trajectory around the ship thing. These are the bottom mounted, which this is how they solve the problem, because if there is a this is how they have been put into the sea, this thing here, so they are only this thing here to be secured by the action of the fishing activities in the area. So because this is the way how it has been lost, and this helps to avoid the damages by the fishing activities. This is the mooring mounted. If you put it on the mooring, here is how it's put on the mooring in the polar areas. Huh? Okay. This is how and where is an IDCP used, and I told you already the type of usage what we have been doing in inlets. This is what has been done. Fisheries. These are all these applications in coastal and ocean engineering, navigation safety, fisheries, biological oceanographic. Biological oceanographic here is not mentioned. This possibility to study the zooplankton biomass. Okay, so that's I would stop here with ADCP, and next time we'll try to squeeze the last lecture and finish the instruments, and this would be our last lecture, because our meeting for the exam. So that's it. Have a good time. See you around, and see you the day after tomorrow.